Okay, welcome to my talk about entropy of a quantum channel. This is joint work with Gilad Gour, who's at University of Calgary, and I'm Mark Wilde. I'm at Louisiana State University. This is a paper that we put up on the archive, I guess, nearly 2 years ago, and we submitted it for review at ISIT, and we're pleased that it was accepted. It's in review at a journal also, and should soon be accepted. Okay, so let's get started with some motivation. The entropy of a quantum state is really a fundamental notion in both physics and information theory, and it actually has a number of interesting physical meanings. But then when we reflect a bit, we realize that a more fundamental notion than a quantum state is a quantum channel, because all the objects involved in quantum mechanics, states, evolutions, measurements, discarding of systems, these are all particular kinds of quantum channels, and so it suggests we should shift the focus to quantum channels. So that's what we're doing in this work. And actually, more generally, we're seeing this kind of trend going on in quantum information theory, and in the context of quantum resource theories. A lot of the focus now is moving to understanding quantum channels as resources. Okay, so we want to go back and establish a meaningful notion of entropy of a quantum channel. So that's our goal. So let's review a bit. This is something I think everybody attending the quantum session at ISIT would be familiar with. But anyway, the entropy of a quantum state is defined like this. This is often called von Neumann entropy. And it has at least two operational interpretations. One in terms of quantum data compression, how many qubits you can compress a quantum state down to in an asymptotic sense. But it has another interesting meaning in the context of entanglement manipulation of pure bipartite states. It's in some sense a unique entanglement measure for bipartite states, bipartite pure states. Okay. We can think of the entropy of a quantum state in terms of a more general measure called quantum relative entropy. And this appears a lot in quantum information theory also. The relative entropy between states rho and sigma is defined by this formula, trace rho log rho minus log sigma. And what we can do is we can rewrite the formula for quantum entropy in this way. The log of the dimension of the state minus the relative entropy to the maximally mixed state. And so it gives you a way to think of entropy as being like a comparison between your state and the maximally mixed state. So how far is it from being maximally mixed up to this translation factor and a minus sign. Okay, so what we do is we take inspiration from that latter formula for entropy, and we use that to define entropy of a quantum channel. So the relative entropy of quantum channels, if we have two general quantum channels, N and M, we can define it in this way. This is a way that Milan Masoni, Tom Cooney, and I defined it a few years ago. So what you do is you optimize the relative entropy with respect to all possible states that you could send in to the channels to try and distinguish them. You also allow for a reference system, because in quantum information, we know that that can help. In classical information theory, it does not help. But in quantum information, it can, because of entanglement. Okay, and then when trying to generalize that formula, we want a channel or dynamical generalization of the maximum mixed state. What is that? It's the completely depolarizing channel. It's the channel that just discards the input and replaces it with a maximally mixed state. So we also call that replacer channel. Then the formula we have is this. You just take the log of the dimension of the output system of the channel minus its relative entropy to the completely depolarizing channel. And that is our proposal for entropy of a quantum channel. A similar notion was proposed in a concurrent paper of Shao Yuan around the time we posted our paper to the archive. Okay, so let's get into a bit why this is an interesting definition for entropy of a quantum channel. Our approach is that it satisfies several axioms that are interesting for entropy of a quantum channel. And it also satisfies an asymptotic equipartition property, and it has an operational meaning. And so we think it's a good definition. Okay, so let's give a little bit of background on that. For that, we need the notion of a quantum superchannel. What is a physical evolution of a channel? That's what's known as superchannel. Okay, so it's the most general physical transformation of a quantum channel. It's a mathematical object that accepts as an input a quantum channel and outputs a quantum channel. In information theory, we use superchannels all the time when we encode and decode quantum information in a channel. So you have the original channel of interest over which you're trying to send information. The way that you transform that channel is you do an encoding and decoding, and that is a particular kind of transformation of the channel. Often you're trying to take a noisy channel and convert it by means of this encoding, decoding, aka superchannel, into an ideal channel. Okay, so writing things down, we need a few symbols. The superchannel, it takes as input a quantum channel going from Alice to Bob that outputs a channel that I'll call K, I guess going from Charlie to Dan or some other people. Okay, so you can specify axioms that are desirable for a superchannel. And once you do so, you realize that every superchannel can be realized in terms of pre and post-processing channels. And so then we have a diagram that looks similar to what we think about in information theory. The main thing is that with this pre-processing, there's a quantum memory system that gets passed along from the pre-processing to the post-processing. And then the channel that you're transforming gets plugged in here into the diagram. And so you draw a box around the whole thing. That's now a new channel that is a physical transformation of the original channel. Okay, so for entropy of a quantum channel, what is a reasonable axiom that if a superchannel is uniformity preserving, then the entropy cannot decrease? So by uniformity preserving, we mean that the superchannel preserves the completely randomizing channel, the completely depolarizing channel. So if you input to the superchannel, the completely depolarizing channel, if it's uniformity preserving, then the output is a completely randomizing channel. So why is that reasonable? One justification is that if we look back to states, entropy does not increase under the action of a unital channel, which is a channel that preserves the maximally mixed state. So this represents a quantum generalization of that. Another property of interest is additivity. We view this as an essential axiom for a channel entropy measure, and that's that if you evaluate the channel entropy function on a tensor products of channels, it should be the sum of the individual ones. So the definition that we propose satisfies that. And then another one is kind of a self-consistency check. As we said at the beginning, a state is a particular kind of channel. So a state is a channel from a trivial Hilbert space in which the only density operator is the number 1 to the state space on which the state is, so the space of density operators. So for all such kind of trivial channels in which the channel is actually a state, the channel entropy measures should reduce to the von Neumann entropy that we mentioned at the beginning. That is the case for the channel entropy measure that we proposed. So it's like a consistency check. We can generalize von Neumann entropy to Renyi entropy. That's something that's commonly done in both physics and information theory. In information theory, we know that Renyi entropies have operational meanings. And so that's something we looked at in this paper as well. And so what we used was a similar recipe, starting from the sandwiched Renyi relative entropy of quantum states, which is one Renyi generalization of relative entropy. This leads to sandwich Renyi divergence of channels. This is also a quantity that Milan, Missoni, Tom Cooney, and I proposed some years ago. And then we used a similar recipe to define the Renyi entropy of a quantum channel. So again, it's the difference between the log of the dimension of the output and the Renyi sandwiched channel entropy to the completely depolarizing channel. You can check that this definition obeys the same axioms. It does not decrease under the action of a uniformity preserving superchannel. It's additive and it reduces to states. Okay, so there's another property of interest for this quantity, and that's an asymptotic equipartition property. Okay, so to talk about this, we should think about a metric on channels, which allows for comparing them and has an interpretation in terms of distinguishability. One such common metric is the diamond distance between channels. We're not going to use that here. We're instead going to use something called the sign channel distance. It also goes by the name purified channel distance of two channels. And it comes about from this formula for states. And so this is a metric on states, and it follows this quantity is a metric on channels. So what we do is define a smooth min entropy of a channel. The idea behind this is similar to what is done for states. For states, the min entropy is the negative log of the maximum eigenvalue. It's related to guessing probability. And then you smooth that quantity over nearby states. And that concept has found a lot of use in quantum information theory. So what we're doing here is the channel generalization of that. The min entropy of a channel itself is, if we look in the previous slide, that's actually the alpha infinity limit of this quantity, okay? And so what we do is we take that quantity and we smooth it over nearby channels, where nearby is with respect to this sign distance. Okay, and then what we can show is that an asymptotic equipartition property holds. So if you pick an arbitrary epsilon, we have this inequality that in the asymptotic limit, this inequality holds, that it effectively looks like the entropy of a channel, okay? And for the opposite inequality, it's a technical matter at the moment. We take the limit as epsilon goes to 0 as well. And then we get this inequality. Okay, so we have this asymptotic equipartition property, which is a nice property to hold for entropy of a quantum channel. And then the other thing that we have is an operational interpretation in terms of something called quantum channel merging. Okay, so in this protocol, what is the goal? If we have a channel from Alice to Bob, we can always purify it, and we get an isometric extension of the channel. And the goal of the task is for the receiver of the output of the channel to transmit the system that he possesses to the environment. So it's like this person is trying to merge his share of the channel with the environment share, okay? And to do so, we allow for a one-way LOCC protocol from the B party to the E party. And we allow the consumption of entanglement. And we're also interested if entanglement can be generated in this process. Okay, so this is the ideal thing we're trying to do. This is the way that we actually implement it in a protocol. And what we find is that the rate at which entanglement can be gained in this process is equal to the entropy of the channel. And so it gives the entropy of a channel an operational meaning. And so we thought that was interesting. Okay, so I'm going to wrap this up now. Our conclusion is that we define this concept of entropy of a quantum channel. We consider it to be a fundamental notion in quantum information theory. We showed that it satisfies these axioms, like non-decrease under a uniformity preserving superchannel, additivity, and reduction to states. We showed that it satisfies an asymptotic equipartition property. It has an operational meaning in terms of this protocol of quantum channel merging. I should mention that quantum channel merging is related to a well-known notion called quantum state merging, and it represents a dynamical generalization of that concept. What do we want to do in the future? At least one thing we'd like to do is establish the operational meaning of entropy of a quantum channel in the context of a resource theory. There's related work done on this that's similar, that was done by Philippe Feist, Mario Berta, and Fernando Brandao about thermodynamic capacity of quantum channels. But that doesn't it doesn't quite give an operational meaning to the entropy of a quantum channel, but perhaps some of the ideas there could be used to do so. Okay, thanks for listening to my talk. I hope everyone stays safe in the pandemic, and I'm really looking forward to seeing everyone at the next year's ISIT. Thank you.